Okay, let's move on. So the next speaker is Nakul Gangolli, who is talking about the constraining reionization in progress at redshift 5.7 with Lyman-alpha emitters.
Yeah, hi everyone. Thank you, Professor Ricci. Hi everyone. My name is Nakul Gangolli. I am a third-year graduate student at UC Riverside. I work with Anson D'Aloisio. And so today I'll be talking about how to constrain reionization in progress at redshift 5.7 with Lyman-alpha emitting galaxies. And to kind of give some broad context for what I'll be talking about today, there have been models that have been proposed which have reionization ending as late as redshift 5, which is actually very convenient for a lot of us since there are surveys already out there like SILVERRUSH which can observe LAEs at redshifts 5, 6, and 7, which means that they could very well be observing the tail end of the reionization process. And so what I want to do in this talk is to revisit large-scale structure statistics of LAE in the context of these late reionization models. And so to kind of further motivate what I'll be talking about large-scale structure, if we take a look at the SILVERRUSH fields from the SILVERRUSH 1 paper, we can see how there are some fields which display this large field-to-field variance as well as intrafield variances. For example, at redshift 6.6, we can see how UD XSDS and UD Cosmos have this large variation in their densities. Whereas in DLA SIN 1 at redshift 5.7, half the field is quite LAE rich and the other half is very LAE poor. And so the question that I kind of wanted to ask was, accounting for inhomogeneous selection effects, what are causing these large-scale density variations? Can they be explained due to just large-scale structure evolution alone, or does these large variances necessitate the need for neutral gas left from some late reionization model? And if it's the latter of the two, can we determine what the neutral gas fraction is? And if so, what tools are most adept at answering that question? And so what we first have to do is construct our mock LAE surveys. And the way we do this is we populate halos in a 1 cubic gigaparsec size box from the MDPL survey, or from the MDPL simulation, such that we can get a large statistical sample of SILVERRUSH size fields, because the SILVERRUSH size fields are hundreds of megaparsecs off into a side. And so that's why we needed this huge box. And then the method that we use to populate those halos with LAEs is the method outlined in Weinberger et al. 2019. And I won't go into too much detail about what they do, but the important aspect of their modeling is that we implement a beta parameter, where this beta parameter in essence connects the circular velocity of a halo to the velocity offset from the Lyman-alpha line redward of the systematic. And as an example, here is a Lyman-alpha line. This is a Lyman-alpha profile where the line offset is centered at about 100 kilometers per second. Then to model our early and late models of reionization, we tune the neutral fraction of the IGN using the excursion set model of reionization. And so what we do is for our early case, we set the neutral fraction to be 0% at redshifts 5.7 and 6.6. And then our late models include a 10% and 30% neutral fraction at redshift 5.7 and a 25% and 50% neutral at redshift 6.6. Then what we do is we tune beta specifically such that we make sure that we match our observational constraints, where those constraints include the Lyman-alpha rest frame equivalent width, the LAE luminosity function, and the 2-point correlation function. We also make sure that we keep our mean LAE surface densities fixed between all our models, and that will kind of become an important caveat later on. And we set the mean LAE surface densities to be the same LAE surface densities in the SILVERRUSH fields at their corresponding redshifts. And at the end of the day, we are left with 1,000 mock catalogs for each of our different models, for a grand total of 6,000 fields of view. And so to kind of give an example of what we're dealing with, here are some LE catalog maps with redshift 5.7 on the left and redshift 6.6 on the right. And I show them with their given neutral fractions. And what we kind of begin to see is that where these points are the LAE and the shaded regions are the neutral gas, is that the more neutral gas that we seem to add, the larger these voids are getting in the LAE large-scale structure distribution. And to kind of make that point concrete, if I blink between the two, we can see how not only are the voids getting bigger, but the neutral gas is in essence relegated to those voids. But also that the LAEs seem to also be in essence sequestered to the high density regions in more neutral scenarios. And this is a direct consequence of us keeping our mean LAE surface densities fixed. What ends up happening is that the LAEs that are getting obscured in the neutral regions of the IGM have to be compensated for to make sure that LAE surface density stays the same. And so the ionized regions of the IGM become much, much more transmissive to the Lyman-alpha line. And so then this comes back to the first question that I wanted to try to answer, was whether or not the large-scale structure evolution could explain the wide field-to-field variations that we see in the fields, or that if that extra effect from neutral gas is needed to account for the variations. And so what we do is something that we call the split screen variance, where in essence we take a given field of view and subdivide it along axes of symmetry such that we get roughly equal area and roughly similar shapes. And then what we do is we find the magnitude of differences between the different fields of view and normalize by the average surface density. And while this becomes quite simple in the case for our square fields, this is a little bit more difficult in the case of the SILVERRUSH fields, which are a little bit more irregular in shape. But there are ways to kind of subdivide the field, like indeed deep in 2.3 that we do as an example here, where we kind of cleverly find different axes of symmetry and split the fields in different ways. And at the end of the day, what we find is that the SILVERRUSH split screen variance is actually consistent with evolution from large-scale structure alone and doesn't necessarily need neutral gas to explain the variations. But that being said, the more neutral gas that we seem to add, the wider these distributions seem to get, making it more likely in neutral cases to find these large intra-field variances, or these wide half-field differences in the LE densities. And so then that brings me to the second question. Well, okay, let's assume that there is neutral gas. Is there a way to find out how much of it there is, if it is there? And so the first statistic that we use is the void probability function, which has been looked at, before. But in this context, we look at it in late Reionization history, where in essence, the VPF is the probability of dropping a circle with radius r, and then the probability that circle contains 0 LAE. And so I show what that looks like for different scenarios, where this black line is the Poissonian distribution, where you randomly kind of throw points onto a grid and calculate the VPF for those points. And what we find is that when we start accounting for large-scale structure statistic, or large-scale structure formation, these voids get larger. But then when we add more neutral gas, as we saw before, these voids seemingly get larger and larger. And this makes that qualitative fact more quantitative, where the voids are getting larger with the more neutral gas that we're adding. And that's because the LAEs are getting obscured in those low density regions. And I just as a caveat, these error bars that we see here we seem to be due to cosmic variance. We do the same analysis at redshift 6.6, but what we find is that there are actually larger voids at redshift 6.6 than at 5.7. But that's more so a thing because there's a lower LAE surface density redshift 6.6, and you can kind of see how the Poissonian distribution changes quite significantly because of that, and how all these curves change with respect to that Poissonian distribution. We also do deal with larger neutral fractions, but those are really only applicable to the blue and green lines. But at the end of the day, we see the very same idea, where with more neutral gas, the voids seem to grow in size. And so while I talked about how adding neutral gas enhances the sizes of the voids, but now what about what's happening to these high dense regions? Can we quantitatively explain what's happening there? And so what we do here is use the peak probability function, which is the high density analog to the VPF. And it's a probability of randomly placing down a circle with radius r and enclosing a region with some density greater than a threshold density, which we set to be 2.5 times the mean LE density of redshift 5.7 and 2 times the mean LE surface density of redshift 6.6. And what we see is that, yes, there is an enhancement in the apparent clustering of the LAE, where these dense regions are getting more dense. Unfortunately, the error bars from cosmic variance are actually very large, and we attribute these to large correlations between the radial bins. And thus, the dense regions tend to be closer to or within other highly dense regions, which makes it extremely difficult to use to constrain the neutral fraction. And we again do the same analysis of redshift 6.6, and we see the same thing. The apparent densities are getting higher and higher, but the error bars are quite large. And so now to kind of come back to the last question of how do these statistics stack up? Which ones are most adept at answering how much neutral gas there is? While the peak probability function doesn't do as well, what we do is we'll compare the void probability function to the 2-point correlation function, which is currently the most popular probe used today. It's kind of the gold standard right now. And what we do is we assume two different survey strategies: a SILVERRUSH-like survey where we sample 4 to 5 fields at a time, and a 10-field survey where we sample 10 fields. And then what we do is we bootstrap resample each case 10,000 times over and construct a chi-square distribution for the completely ionized IgM. And then what we do is we assume that we observe a curve which corresponds to a late reionization ending model, which is 30% neutral at redshift 5.7 and 50% neutral at redshift 6.6, and calculate the p-value of observing such a curve in a completely ionized IgM. And what we end up finding is that at redshift 6.6, the void probability function is about as well as the 2-point correlation function. But at lower redshift, at redshift 5.7, the VPF actually just does a better job than the 2-point correlation function. And this actually holds while we account for contamination effects as well. We test for contamination and find that it affects both of them roughly about equally. And so the intuition as to why the VPF might be doing better at lower redshift than at higher redshift is that at the tail end of the reionization process, the neutral gas is relegated to the voids. And since the large scale structure has more time to essentially evolve, those voids become more enhanced by the neutral gas present in the IgM rather than being more dispersed earlier on. And so I'll kind of conclude my talk there. I'll leave up a summary slide, and thank you for your time. I'll take questions.
Great, thanks, Nakul. All right, so then, yeah, please go ahead, Anselm.
Yeah, so there is already one question here. How do you model the escape fraction of Lyman-alpha photons on these large scales to generate the mock maps?
I'm sorry, could you say that again?
How do you model the escape fraction of Lyman-alpha photons on these large scales to generate the mock maps?
Oh, so what we do is we implement an IgM attenuation code. So if I go back here, similar to what happens in this curve. So what we do is we shoot skewers through the IgM and assume that as we shoot skewers through it, the neutral fraction, in essence, when we shoot a skewer through the IgM. Actually, can I get back to you later on that? I'm sorry. I need to.
Okay. Yeah. Sure. Yeah. Please, if you have any questions, please put them in the Slack.
Yeah. Sorry, I need to get back to you on that. I'm kind of getting lost. I'm sorry.
Right. So I think now people are writing up the question, but okay. In the meantime, so let me ask a question. So short question. So I think that you assume the velocity shift of Lyman-alpha for 100 km per second.
Oh no! So we use the beta parameter to tune the velocity offset of the Lyman-alpha line.
Okay.
When that's related to the circular velocity of the halo itself.
Okay. All right. So yeah, I thought it is fixed. So okay. All right.
No, it's not fixed. We change it.
Good. Right. So some more questions. Yeah. If not, I think the time is good. So all right. So yeah, let's thank Nakul again.